So we've pretty well established that the reason why most of you are taking this class is because you have an abiding desire to learn about the world of physics, which is nice. Except, let's face it, at this point, most of you are probably primarily focused on getting ready for your first test. Unfortunately, I have, along with that responsibility, helping you out to do that, I have other responsibilities. One of which is being sure that you actually understand the conceptual underpinnings of the theory that we're dealing with. I need to show you where the equations, for instance, have actually come from. I need to show you that, in fact, this is not just magic that Mr. Fletcher has made up and dumped on you. So this particular video is designed to show you where the kinematic equations have come from. This is not something that you should necessarily memorize. I'm not going to ask you to reproduce this on a test. So from that perspective, it's not going to be very useful for you as far as the test goes. Although, if you don't pretty well understand what the underpinnings are, it's probable that your use of the equations on a test, especially if you run into a fairly difficult problem, could be somewhat stunted. So I want you to just sit back, listen to what I have to say, just let it flow over you, and if you have questions about it, you can ask me in class. Kinematic equations are predicated on a constant acceleration. Constant acceleration means that the velocity versus time graph is going to be linear, which in turn means that if you take any time interval and you figure out what the slope is of the function over that time interval, that slope, which is going to give you what the acceleration is always going to end up being the same. The acceleration is constant during the motion. So the first kinematic equation is simply just a statement of the slope of the velocity versus time graph. Clearly this would be useful if you were looking for the acceleration of some object and you knew what the initial and final velocity was over a time interval. That isn't always the information you know, though, and it isn't always the information you're looking for. So there's another form that you often run into, and you can get that form by manipulating this. You simply take the delta t and bring it up, and you take the v1 and bring it over, and you end up with this relationship right here. Effectively, what this relationship says is that if you're trying to find out what the velocity is at the end of some time interval, and you know what the velocity is at the beginning of the time interval, if you add that beginning velocity to the way the velocity has changed due to the acceleration, which is what this a delta t quantity will give you, that will tell you what the velocity is at the end. Both equations, same equation, just different forms and different presentations. Don't memorize them both. You only really need one, but in any case, this is the first of your kinematic equations. So the second kinematic equation is again predicated on constant acceleration. This time we're looking at the area under the velocity versus time graph. So here we have our velocity versus time graph. Here is the area underneath, which we've broken up into convenient sections. The area of the bottom portion is just going to be that of a rectangle, which is going to be the base times the height, where the height is just v1. The area of the triangle is just going to be 1/2 the base times the height, which if you put in the variables and manipulate, you come up with a relationship that looks like that. If you add those two areas together, you will end up with the net displacement of the body, or if you would prefer to write it in terms of the coordinates, you can take the fact that the net displacement is equal to the change in the initial and final coordinate, put that up into the displacement expression here, do a little manipulating, and end up with the expression that you see here. This relationship is interesting and useful. It effectively says that if you want to know what the coordinate is of the body at time t2, and you know what the coordinate of the body is at time t1, if you add that initial coordinate to how the coordinate motion changes due to the fact that the body was initially moving with some velocity v1, and you add that to the way that the body's position changed due to the fact that it was accelerating over the time interval. If you add up all of those changes of position to the initial coordinate, it will give you the final coordinate. In any case, these two relationships, either one, whichever one you choose to memorize, characterizes the second kinematic equation. Third kinematic equation is also predicated on constant acceleration and is related to the area under a velocity versus time graph. It's a little bit complicated, the derivation is. It's nothing that you are ever going to have to reproduce on a test. So I'm going to go through this fairly quickly. I'm doing this, if you remember, primarily because I want you to know that these relationships actually have a basis in reality. They aren't just relationships that I just sort of pulled out of my ear. As I said, I'm going to go through this fairly quickly just so you can see where the relationship came from. But you don't need to worry about, knowing the ins and outs of it all. You're never going to be asked to reproduce it on a test. So here we have a velocity versus time graph. Here is the area under the curve. If we take this little section, this little triangle here, and cut it out and flip it over and put it in right here, it will fit due to the symmetry, and you will end up with this nice rectangle. Okay, the rectangle will have an area to it. The area will be related to the base, which is delta t, and the height, which is going to end up equaling the average velocity over that time interval, which is just going to be v1 plus v2 over 2. So the area under the curve is going to be this quantity right here. Area under a velocity versus time graph is equal to the change in the position of the body, the displacement. From this relationship, we can solve for delta t, which seems bizarre, but that's what you have to do. So you come up with this relationship for delta t. So if you start with the first kinematic equation, which is delta v over delta t, and you substitute that delta t term in that we just came up with, and you manipulate, you can come up with a relationship that looks like this. You bring up the 2 delta x up to here, you multiply these guys out, you get v2 squared minus v1 squared, which brings us down to here, and then you go ahead and you take the v1 squared term over, and you end up with a relationship that looks like this. Okay, this is the third kinematic equation. It effectively says that if you know the velocity at the second point in time, you square it, it will equal the velocity at the first point in time of the interval squared plus 2 times the acceleration times the change in the position, the coordinate of the body over the time interval. So the kinematic equations are essentially a reshuffling of variables in a constant acceleration circumstance. So here you've got velocities, times, and accelerations all in one relationship. But you don't have anything that has anything to do with the coordinates. So if you were looking to see where a body was at a particular point in time, you wouldn't use that relationship right there. Here you've got coordinates, you've got time, you've got acceleration, you've got an initial velocity, you don't have the final velocity. Here, final velocity, initial velocity, acceleration, position change, no time. So the approach for using this kind of a problem, usually you make a little sketch so you can put the information that you know down into the sketch so that it's visually in front of you. You identify the variables that you know, you look to see what you're trying to figure out, and you try to find an equation that's got what you know and what you're trying to find out, and then you just plug and chug.